Hello, everyone. Today we're going to be talking a bit about some basic GIS concepts, maybe a little bit of a review for some people, and getting into geographic information systems, what they are, how they work, and how we use them. So, really quick, we're going to learn how to analyze spatial data, create maps using geospatial software, produce high quality graphics, including maps, charts, and other forms of media, apply skills in remote sensing, geographic information systems, and data science to solve a problem of your own design. And I want to stress a growth mindset when learning and reinforcing these concepts. It takes grit and perseverance to sometimes weather the frustration that comes with learning challenging new things. So, with that, why do we even care about GIS? Well, using computer-based tools to study our planet and understand our environment allows us to advance knowledge as we know it and solve problems, create better societies. So this illustration shows the seasonality associated with Earth. Via satellite images, these are true color images showing the changes in seasons in the north. You can see lots of snow changing, moving up and down the latitudes. And towards the center of the map, you can see forests in Africa, South America, North America, and Asia growing and changing locations with the seasons. So using geospatial technologies allows us to derive these insights and observe changes in our planet as they happen. Another reason to use GIS, by looking at just the area of these two shapes, they would be identical. And so by plotting them on a two-dimensional coordinate system, X and Y, we can see that they are different, right? One is a square and one is perhaps a river or a road or some kind of linear shape, but a polygon too, right? So plotting these things speaks very deeply to the visual parts of our brain and lets us understand and pattern recognize and unlock insights about data that we might not otherwise. And I just mentioned pattern recognition. So can you find the pattern in these data? Take a quick second. They are separated between odds and evens, and plotting them on a map lets us deduce those patterns and correlations quite quickly. Now, I mentioned understanding changes in our environment. We can monitor these changes over time using remote sensing technology and satellites and other vehicles. So this shows the changes in a sea called the Aral Sea from about 2000 until 2020. You can see the date in the bottom left corner. Sorry, it's 2000 to 2011. And, measuring this type of change on the ground would be so impractical by a single person, right? You would have to go out every day, walk vast distances, look at the scale bar at the bottom right of the images showing 50 kilometers. Using this technology allows us to monitor the Earth and understand changes at an unprecedented level of detail. So getting into some key GIS concepts, location, right? Location is a position on the surface of the Earth. You can assign a location to almost everything. You can put a thing on a map once you have a location. We can define locations both absolutely and nominally, right? So an absolute location we define using coordinates, either XYZ coordinates, like a Cartesian coordinate system that you're probably used to from geometry. We can also use latitude and longitude coordinates, which are the geographic coordinates. You're probably familiar with these through GPS, right? Tracking your location based on a phone that communicates to satellites that triangulate your location based on the transmissions to multiple different satellites. It's pretty amazing when you think about it and step back and appreciate how it works. We'll get into that later in future lectures. Of course, you can also, in contrast to an absolute location, have a nominal location. So relative to another object, like west of campus, east of Eden, and so on. Direction, right? Concepts we're very familiar with. Where is the feature or phenomenon relative to another reference point, right? The reference point can be anything. So I'm heading south, right? And in these case of the cardinal directions, the reference point, the assumed reference point is the North Pole, right? Or the equator, basically. We've agreed upon this coordinate system for the cardinal directions, right? They're relative to the North and South poles. But you can use anything as a point of reference, right? East of Slough, south of Antarctica. I don't know if you can go south of Antarctica. Yeah, you get the picture. Distance. How far apart are two locations? Again, this can be nominal, like close or far distances, or absolute, like a mile or a kilometer or a foot or a millimeter. We can easily calculate distance on a flat surface, right? X coordinate minus, the 2x coordinates, difference of those squared plus the difference of the two y coordinates squared, square root of all that. It's basically the Pythagorean theorem, if you think about it, is the distance. But three-dimensional distances, like spheroidal objects like our Earth, are complicated, and you need calculus to do this correctly. So we will make a simplification and use a technique called map projections and coordinate systems to make accurate distance calculations on three-dimensional objects, and we'll get into that later this lecture and in future lectures. There's also space and navigation, right? So space is absence of things. We have lots of space on the Earth. You can also think of topological space, so how various things are related to each other, like a subway map, right? The subway nodes are connected to each other, and certain stations you can connect to multiple lines. So that's kind of a network, or like a graph, or a topology. So it's convenient to think in that sense sometimes. There's also navigation, right? So moving through space, be that a topological space or a physical space. So GIS systems really work in layers, and each layer represents a real-world phenomenon. So you might have a layer describing land use. You might have a layer describing elevation of each area. You might have a layer describing the locations of businesses, of streets, of telephone poles, and so on, right? Each layer represents a unique phenomenon's distribution across the landscape. But these layers can also have what are called attributes, right? So they describe those layers and the features, the so-called features within them more descriptively. So you can think of this as basically the columns in a spreadsheet. So a data set describing the locations of cities might have a column called city, where you would list the names of the city, and a column describing the latitude and longitude of each city, which we can render on a map. Speaking of rendering maps, there's a few sort of different categories of maps that we deal with commonly. First is a reference map. It just shows the location of an object. You've also got a thematic map, which shows how something is distributed across the landscape. In this case, you can see some metric distributed across global countries. Now, you also have interactive or dynamic maps, and those are things that update based on inputs from the user. So, this is kind of like a web map that you can interact with, like Google Maps, or a direction, right? So a mapping application, also like Google Maps on your phone, that might guide you to your location and updates based on your position. So all maps basically have a scale, right? And the scale of a map is the factor by which you kind of shrink down the real world to fit it on your screen. And, you can depict this scale in a couple of different ways. The most common way is with a scale bar, right? So it will show you a little length on the screen that you're looking at, and that little length will correspond to a real world distance, often in like kilometers or miles. And so you'll that way you can get a sense of how big the objects in the map really are. The other way to express a map scale is with what's called a reference fraction, which is basically just a ratio. In the little example here, which I'm mousing over, you have a reference fraction on a USGS topographic map of 1 to 24,000, which means essentially this map is shrunk down by a factor of 24,000. And if you blew it up by that same factor, it would be the real world units. And you've also got a scale bar there, so it's kind of convenient to look at one of these and think about how both of those communicate the same thing. So really quick, reviewing some basic concepts in GIS and computing. So data, right? We work with a lot of data. Those are facts and measurements and characteristics of something of interest. Information are things that we learn about those data, knowledge or insights that are acquired through analysis. Spatial data are data that describe geographic and spatial aspects of something. So, how is something distributed across the world, across a county, across any kind of area? Facts and stats collected together for reference. Metadata, in contrast, are data about data, right? Like what that data is, who it was collected by, what were the instruments, when does it correspond to, what do we need to know about this data to make sense of it? What are the units, right? If there is a coordinate system, what's the projection? We'll talk about that more. So, the who, what, when, where, why, and how of the data is contained often in the metadata. So computers, how do computers work and how to store files? So computers basically store files in a tree-like format. I think we've got slides on that here. And you can think of the first directory, the top level directory, as like the root. So the C, this corresponds to the C directory in Windows, and it's just a slash in Mac. And everything from that directory kind of branches out from there. And so you can have this like nested branching structure where the full path of a file refers to the tree of directories that you'd have to traverse to get there. So for instance, I'm showing a file on my desktop in a folder called Grants and in another folder called Schmidt Futures. And the full path of that is as follows. It's right, users, my username, desktop grants, Schmidt Futures, and the file name. So that's how computers store files. And they tell, the computer knows which program to use to open the file by the file extension, right? Those are the letters after the dot in the file name. And some common geospatial and GIS file extensions are listed here. We've got SHP and an accompanying few files. We've also got some KML, TIFF, GPKG, JSON, GeoJSON, text, HDF, NC. You may encounter all of these during your GIS escapades. So the best practice is to really organize your GIS files and all of your files, rigorously. And this helps, you share your data with others. It helps yourself stay organized. And it's actually a gesture of kindness to your future self to keep things organized. So you can find things later. And this has saved me a lot of time. So instead of naming something like document.docx, name it something descriptive, like the name of the class, the assignment, the draft, right? And store it in a folder with the name of the class. Maybe make a folder in that folder called assignments. So keep things organized and you will thank yourself. Your future self will thank your past self. And it's really sort of a beautiful moment when I'm like, oh, thank you, past self, for leaving this in a good condition for my future self. So, okay, speaking of files, here's a typical file, a data file that you might read into any sort of software, right? It's a CSV or an Excel spreadsheet. CSV means comma separated value. So this file has some headers, right? These are also like column names. They can be called schema, fields, other things too. So these are what we call the headers, right? They're the names of the columns. Yeah, you can call them attributes in GIS also. So these are the rows, right? There's 3 of them, and they contain essentially the data. In GIS, we call these the features. The columns include both the column header and the data within each column. So the country column has the data France, Brazil, and Australia in this example. Now each column has a data type. What we mean by that is what is the similarity essentially between the values in that column, right? So think about how the values in the column population might be different than the values in the column country. Obviously, population is going to be a number and country is going to be like the name of a country, like a label or category, right? Different types. These are numbers, these are letters. So basically, there are a few different of these data types. You can either have either a true or a false statement, like a light switch, and that's called a Boolean or a bool. You can have a string, right? Like alphanumeric text, like one of those country names or anything really in quotation marks. Usually it's denoted by quotation marks. You can have numbers, so they can be numerical values, often latitude, longitude coordinates. You can have them as integers, so like whole numbers, 1, 17, 491. And you can also have decimals, right? Also called floating points. So these are like 20.2, 7/8, things that can't be a whole number, and negatives. So those are the data types. So we can also have, continuous data, which are numerical values, or discrete data, which is basically categories, limited number of groups or categories. And if you think back to our example, here our country column is basically discrete or categorical. And our population category is basically continuous, right? It can be like between 0 and some unknown large number. There's also the concept of levels of measurement. The 4 of them are nominal, ordinal, ratio, and interval, and they also kind of describe these data. So let's talk about those briefly. Nominal levels of measurement are basically names or identities of objects, like the names of states. Everything has a different name. This is like our countries column, text values, but they can be like tax numbers, social security numbers, something like that. And they're usually labeled on a map. And that is, described by land use is a good example. So you can have different categories of land use. You can have commercial zoning, residential zoning, so on, manufacturing areas, office parks, all kinds of zoning. The urban planners know all about these things. And those are nominal categories of land uses. There's also what are called ordinal data. So those are ranked categories that are based on some kind of measure, but it might not be like a linear or an obvious scale what the ranking criteria is. So an urban area like villages, towns, or cities, like what even are those categories and how do we categorize them? Or like students, well, we know that, cities are bigger than towns, which are bigger than villages, but we don't know where the breaks are. No numerical values, right? Grading. So we know that there's a hierarchical grading system, but there's no like numerical values, maybe like soil types. And so a nice example here is an affordability map by county here. And you just have this as low, medium, and high. And obviously some quantitative data was used to get to this metric, right? Here's basically the formula that they used. But, this just basically ranks these data on a scale of low, medium, high. And so it is ordinal. There are also interval data, and these have a regular scale, but not a meaningful 0 point. So here, a nice example of interval data are temperature data, which are, Celsius, Fahrenheit, and those have a 0 point, right? 0 degrees Fahrenheit, it's pretty cold. It's where water freezes. But that 0 point doesn't mean there's the complete lack of any heat, right? So it's still above absolute zero at Celsius and Fahrenheit temperature scales, right? So uh, that means that it's an interval scale, basically. The absence of the quantity essentially is what differentiates interval from the next scale, which is ratio, which we'll get into. But basically, to sum it up here, any scale that can have like negative values would be an interval scale, like elevation, right? We have a reference point like sea level. And so the elevation that we consider doesn't mean like the lack of any topography, it's just the topography above sea level. And these interval scales, importantly, only support addition and subtraction. So, temperature being a great example is, it supports addition. So 80 degrees is 40 degrees hotter than 40 degrees, but it isn't doubly as hot, right? It's not twice the heat energy. So this is what separates the interval scale from the ratio scale. A nice example of interval that we've been talking about already is temperature. The ratio scale, on the other hand, has a meaningful 0 point that indicates the absence of the actual thing that is being measured. So a nice example of this is precipitation, where if you have a value of 0, it means it did not rain, it did not snow, there was 0 precipitation, right? And all arithmetic operations hold here. So, 10 inches of rain is twice the amount of 5 inches of rain, obviously. But the same can't be said of temperature, right? So ratio data, addition, subtraction, multiplication, and division all hold. And rainfall is the kind of key example here. So, if you think about a data file like this, the headers would be city, sun, temp, and precip. This data file has 3 rows because you don't consider the headers as a row. It's got 4 columns. The delimiter is a comma. The levels of measurement, I think the city would be nominal. The sun, which I think is the number of sunny days, those look like integer data types. And I suppose that would be ratio, because 0 literally means there is the lack of a single sunny day. Temperature, we know, is ordinal, is interval. And precipitation, of course, is ratio. What data types are the columns? We already talked about this a little bit. Sun, temp, and precip, they all appear to be integers, and city appears to be strings or alphanumeric characters. So there you go. Many errors in GIS arise from inconsistent data types or trying to mesh together data types, mesh together data that are not the same data type. So to manipulate these data, they have to be the same type, essentially. So, of course, we can summarize data in lots of different ways, right? So think about the example of the precip or the temp data here. We can take the mean or the median of those data. I would say those are both variables, right? Variables represent a given value or a set of values, like temperature or precipitation in this context. A value is an individual observation. The population is the universe of all possible values for a variable. And the sample is really what we work with, right? Like it's a subset of the population. You'll often see the number or the letter n to describe the number of observations for a variable. Okay, time for a really, really important GIS concept called coordinate systems. And we'll keep coming back to this. Coordinate systems are how we put 3-dimensional objects on 2-dimensional surfaces, like our screens, right? Like the computer screen that you're watching this on. The most common approach of coordinate systems, and the most widely used one, is probably one that you're familiar with, right? Latitude and longitude coordinates. This is called a geographic coordinate system. So we use this to define locations, absolute locations on the Earth's surface. But we are familiar with other coordinate systems too. So think about like the Cartesian plane, X and Y, in your geometry class, right? That is also a coordinate system. So in those geographic coordinate systems, like latitude and longitude, we essentially use degrees as the unit of measure, right? And the reference points in the latitude and longitude geographic coordinate systems are basically the equator and the prime meridian. So the equator corresponds to 0 degrees latitude, and it ranges from 90 degrees north to 90 degrees south, from the North Pole to the South Pole, respectively. Longitude, on the other hand, is measured relative to the prime meridian, which is 0 degrees longitude, and it stretches from 180 degrees west to 180 degrees east. You'll also hear those called negative 180 and positive 180 and negative 90 and positive 90 sometimes. So map projections are essentially how we take three-dimensional data on a spherical Earth and put it on a two-dimensional map. And doing this can introduce distortions in distance, direction, and area, right? So think of an orange that you're unwrapping and trying to flatten the peel. That's essentially how we're looking at the Earth. And, in this example, the red ball is the orange, and the three shapes here, the square, the cone, and the cylinder, are how you might reconstruct that orange peel to look at all of it. And essentially, here's another way of looking at it, right? If we look at this three-dimensional ball from a two-dimensional plane, you've kind of got this weird outward radially angle. And it has some nice properties, but it's not very intuitive on the eyes, and you're kind of missing the second half of the Earth, right? You can only see the top from this angle. If you use this cone, this kind of looks a little different, and it's got some other properties. You're also still missing the bottom half. But there you go. You can totally use the cone, and you can look at, for example, Greenland, how it looks different. It's different shapes in both of these different transformations, basically, or projections. They truly are projections, and they are transformations. Finally, if you look at this cylinder and what the effect of this on the Earth, well, firstly, you can see the whole thing, but look at the size of Greenland. It's changed quite a lot, and this is because this type of projection introduces distortions. We can look at the distortions associated with multiple projections here. So the columns here show different map projections, and the rows show essentially how distorted each area of the Earth gets by using that projection. So by using this kind of cylinder flattened projection called a Mercator, you really distort the poles, the North Pole and the South Pole. And so on, right? There's a compromise associated with using any of these projections. Now, one of the projections that is often very convenient to work with is called the Universal Transverse Mercator. It's abbreviated UTM, and it's great for measuring distances or areas because it has units of meters. And essentially, each little strip of the Earth based on the North Pole and the South Pole, and making little strips between them, has a different UTM zone. And you can reproject your data into these UTM zones to minimize distortions. And we'll see what I'm talking about a little more in just a second. So suffice it to say, California is in the UTM Zone 10 North projected coordinate system, and that will be very convenient to know for later for calculating areas and distances for any data that we have in California. So reprojecting, okay, changing the coordinate system of some data. So this is a geographic coordinate system with latitude, longitude coordinates. This is kind of what it looks like on your map canvas in a geographic information systems program like QGIS. Now, if we change the coordinate system to a UTM Zone 10 North projection, you can see this map changes a lot. And how does it change? Basically, we have placed the North Pole right here, the South Pole right here, and we've put our zone right in between it. And this projection effectively minimizes the distortions in area and distances if we need to measure those things. So changing projections or reprojecting can alter the shape and the look of the data visually. So these are a few different projections, all of them quite common that you might see, that alter how the data look. So here's a very common one called WGS 84, World Geodetic System, 1984. And then here's one of our UTM zones, Zone 11 North. And you can see that there's some distortions, right? There's changes in the areas and the angles and the distances between these shapes. So here's my favorite example to show this. This website, thetruesize.com, essentially lets you compare the size of any country in the Mercator projection to if it were on the equator. So I'm going to type in Greenland right here, and it's going to give me a polygon showing Greenland. And what I can do, Greenland is famously exaggeratedly huge because it's towards the North Pole on this Mercator projection that like Google Maps and everybody uses, right? So you're probably pretty used to seeing this, so am I. But if you want to know the true size of Greenland, you can drag it down towards the equator and notice that it's really only about the size of Mexico. Right? How about that? Similarly, do we really think Antarctica is this big? Is it as big as the whole world? No. I don't think so, right? It's an artifact of a map projection. So let's see if we can grab Antarctica, and of course we can. And what if we drag it towards the equator? Any guesses how big this is going to be? Okay, it's still pretty big, but like, it's not the size of the whole world as denoted by this map projection, which is going totally crazy now. So there you go. That is how projections impact maps, right? And here's another great example. This gentleman with a obviously spherical head, right? If you were to use a Mercator projection, this is what he would look like. So there you have it. And I can just keep beating a dead horse here, right? In the same projection, the distance from one end of Russia to the other is actually, smaller than the distance of one end of Africa to the other, which it, really does not look like from this projection. So, okay, we've talked projections a bit. Let's just talk a little bit about like good map practices. So what should be on a good map? What are you trying to show? Think deeply about it, right? Because you could use different features to represent different types of data depending on like a zoom level or a scale, right? So for instance, you might represent cities with points if you were zoomed out to like a global scale or a country scale. But if you were zoomed into SLO County, you might represent the SLO city boundary as a polygon. right? So think really closely about what the map is supposed to show, what you're trying to communicate, and then really solve for that. But at a minimum, you should include a north arrow and a compass on every map, lat-long coordinates, or projection information. So I would say if you're in a geographic coordinate system, you should include lat-long coordinates. If you're in a projected coordinate system, you should include information about the coordinate system that you have projected in. You should also include a scale bar, right, to orient a user or a viewer as to how much space, real world space, your map is taking up. Labels, of course, label relevant things, and a legend. What do things on the map mean? What are the important features? So all of these maps, all these fundamental features should be on all of the maps. So here's a map that is missing just about everything. That we don't know what this is showing. There's no title, there's no labels, there's no legend. I think there's, those points are different sizes. What are the sizes? It's cool, sure, but it's not very informative. I think the purple are the country boundaries, but it's really left to the person to figure out. So yeah, this is missing just about everything. How about this one? What's this missing? I like this map, it's cool. What is your generic term for a sweetened carbonated beverage, and how does that vary across the United States? Soda pop, Coke, and soft drink. I don't even see soft drink on there. Is it yellow anywhere? I don't know. What do the gradients mean? Like the depth of the red? Is that like more people answered, or it's like more people said soda? Unclear. What do the whites mean? Do the whites mean people were neutral, or just nobody answered, wasn't surveyed there? So like, this is interesting and cool, but I'm just left with so many questions, right? So yeah, I mean, basically I just outlined them. What do these things mean? Like, what are we even looking at? Tell me more about this so I can interpret it. So at a minimum, you should have all of those things, right? Probably a title is missing from here, but it should be included too. North arrow, compass, latitude, longitude, scale bar, labels, legend, and a title. And with that, I think we will take a break